And then we say, well, for the multi-d function, we can reduce it to the 1d function through this trick. Now, we know what happens in the 1d case. We have those two equivalences. So let's look at what do they mean in this case. So I'm going to apply 2, for example, to phi, to this phi here. So to apply 2, what I need to do first is to compute phi prime. Yeah? So phi of t is equal to f of x plus td. What is phi prime of t? Yeah. Well, this is just the directional derivative. Yeah. So remember we introduced this when we were introducing the directional derivative. So this is just let me put it here. The limit when h goes to h goes to 0, phi of t plus h minus phi of t divided h. This is just this f of x plus t here is t plus h d minus phi of f of x plus td divided h, limit when h goes to 0, and then this is just, or this is the directional derivative. So let me write another step here to make it more clear. This is limit when h goes to 0, f of x plus td, let me write it this way, plus hd minus f of x plus td divided h. And now this is the derivational derivative of f in the direction d, but here I am already in f plus td. Yeah, because I'm doing this difference here when what I'm adding is hd. You see? And I divide it by h. And then this is where the gradient appears, because when we define the gradient, we said the gradient is just this directional derivative. So this is going to be the gradient of f evaluated at x plus td. Yeah, and then we get this d transpose gradient of f x plus td. Okay? So that's the derivative of phi. So now let's plug in. So we say phi of t2. So we just replace f of x plus t2d minus phi of t1, f of x plus t1d is going to be greater or equal than phi prime of t1. So that's d transpose gradient of f x plus t1d, yeah, times t2 minus t1. Okay. And now here comes the trick that one knows when it does this proof several times. Let's take t1 equals 0. Yeah. So we take t1 equals 0, what do we get here? F of x plus t2d minus, let me use another color because I don't like this color today. So take t1 equals 0, we get f of x plus t2d minus f of x greater or equal than, then t2 minus t1 is just t2, I'm going to put it here in front, t2d transpose gradient of f of x. Okay? And now, well, instead of having x and t to d, I will call this guy y. So having x, having d, and having any t2 is equivalent to just having some other guy called y. Or if you give me x and y, so given x and y, because that's the theorem that we're going to have, we're going to say let, actually I can take t2 equal 1, and d equal y minus x. Yeah? And then what is this saying? Then we get that f of y minus f of x is greater or equal, t2 is 1, this is x minus y minus x, transpose the gradient of f of x. Okay? And that's the theorem that we have. F is convex if and only if this happens, whether it's x and y. Let's just translating from the 1D case to the neutral case. Okay? And notice that we can hunt on it. Now I realize that that's why I was thinking this was being too complicated. Well, I could have said let's pick t2 equal 1 and t1 equal 0 from the beginning. Yeah, and we just needed the derivative at 0, and that's really d transpose the gradient. Okay? Okay. Questions here? Again, this seems like a lot of algebra, and because it is a lot of algebra, yeah. So, it is. But the important part is that we understand that what this theorem is saying again. I have my convex function. I can only do it in 2 dimensions, but I have my convex function, and then I take that first order approximation, and it's going to be always below the function. Yeah. If the function is not convex, let me do it here. If my function is not convex, it looks like this. Then for some point, the first order approximation is going to cross the function. Yeah? And this is why, I mean, this is a really strong property. It's like a global property. Yeah? Notice that this implies this corollary. F convex and gradient of f of x equals 0 implies x is unrestricted minimizer. Okay. Okay, so let me put a hat here to say that that's a particular point I'm taking. So if I take a point where the gradient is 0, then I got a global minimizer. Yeah, and why is that true? Well, if my gradient is 0, so I plug in here. If I plug in here, when the gradient is 0, if I plug in s hat, so I get f of y minus f of x hat greater or equal than, then I get 0 here. So f of y is greater or equal than f of x hat. Yeah, but this is for all y. Therefore, this is the minimizer. Okay? Now remember, we said if the point is an unrestricted minimizer, then the gradient is 0. Here we're saying the opposite. The one that is not true always. If the gradient is 0, then it is a minimizer for convex functions. So for convex functions, being a minimum is the same as having gradient equals 0. There are no saddle points, there are no maxima. Only minimizers. Yeah?
Isn't unrestricted minimizer the same thing as a global minimum?
Yes and no. So we have to be careful with the language. In some places they say a global minimum for a restricted problem is a point that is feasible and minimizes the function over the feasible set. Yeah, a local minima for a restricted problem also has some meaning there. Yeah, so when I restrict my attention to only the feasible points, this guy is a global minimum. So that in some places they have that definition. That's what I'm putting here, emphasis on unrestricted. Okay? Okay, questions? Okay. Yeah, so this will be a global minimum for the problem without constraints, for minimizing effects. Okay. So this is a strong property, and again, implies something really strong for convex functions. So again, we started with this definition about something happening on the lines. Then we get something that is more global looking. Yeah, I take this hyperplane is going to be always below the whole function everywhere, and then implies something strong about having sufficient conditions for optimality. This is a necessary condition. The gradient has to be 0 to be a minimum, and now it is sufficient for convex problems. Okay, so let's look at the second derivative. Naturally, because I want to see what the third implies in the multi-decays. Okay? So let's look at that. And well, what we really got from here was that, actually, remember this, b prime of 0 is equal to b transpose the gradient of f of x. Yeah. So now the question is, what is phi double prime of p? No, actually for that one, I need to look at the other one. B prime of t, because that is d transpose the gradient of f of x plus gd. What is phi double prime of t? So I will have to do this derivative, okay? So this is going to be, but I will just write the answer, and then we can discuss why that is true. It's going to be the Hessian evaluated at x plus dd times d. So remember, this is a matrix. And then get to here. Okay. Okay, so we get 2 times the transpose gradient of Hessian of f of x plus dd. So check this as an exercise. And then what do we get now from that condition? So actually I'm going to use 3 only for, this is for anything, this has to be greater or equal than 0. That means what? That means now if I do it for 0, for example, so we know that phi double prime of 0 is going to be twice d transpose Hessian of f at x d. Yeah. And I know my function f is convex if and only if this phi t is convex for every x and d. So this means this has to be greater or equal than 0 for all x and d. And what does that mean? So that means d transpose Hessian of f at x d greater or equal than 0. Again, for all, let's fix s. This is for all d. what does that mean about this matrix? Positive semi-definite. Yeah. Remember this means P. Yeah, this matrix is positive semi-definite. Okay? So our second theorem is a function is convex if and only if the Hessian is positive semi-definite. And that again means the same as this one. Yeah, this phi W prime of t greater or equal than 0 meant the derivative is growing, the slope is growing, so it's this U shape. Yeah, and what this says is it's a U shape in all directions. In any point that you stand, it has this U shape. Yeah, it's convex, so it's like this. Okay? And again, it's something about the curvature, the local curvature in all directions. Okay, let's apply those two theorems. And then we're going to do it for the quadratic functions. So we're going to apply first. I did it, but okay, we can write it anyway. So the 1D remember says the f of y minus f of x greater or equal than 1 minus x transpose gradient of f of x. Yeah. And then the question is, when is a quadratic function convex? Yeah, and this is, well, f is convex. This happens if and only if f is convex. Yeah, so we're going to apply this. So what we need to do is to compute the gradient. Now, what is the gradient of f in that case? So we have Px plus q transpose x plus r, and then we get gradient of f of x equal to what? We did this some lectures ago. The gradient of quadratic function is going to be equal to 2 times px, yeah, the quadratic term here, plus q. Yeah, this is a vector. Okay? And then, well, then we can plug in there and see what happens. So let's do that. We did this just from the definition, and it was a lot of algebra. You remember, we just plug in stuff and do a lot of it. So this one is going to be a little bit less algebra, because we already computed this gradient here. And then f of y is just y transpose py plus q transpose y plus r. This minus f of x, y, x transpose px plus q transpose x plus r, and we want this to be greater or equal than y minus x times the gradient at x, that is this quantity here. Yeah, and transpose here. Okay. And then, well, the first thing that happens is constants do cancel. Yeah? Remember, the constant term doesn't matter. And then the linear term is also going to cancel. So let's see that. So we get y transpose py, and then I will write this one, minus x transpose px, plus, and then I get q transpose y, the linear term, minus the x here. And that has to be greater or equal. And then I will split this. So this is twice y minus x transpose px plus q transpose x, y minus x. Or let me write it in the same order that is there. Not that it matters, but y minus x transpose q. Okay? And then this quantity and this quantity are the same, so they cancel. and this is expected. Yeah? The linear term doesn't matter. So for any Q, for any R, the function is convex. The only thing that matters is the P. We already saw that when we did it in the just from the definition. And now we just need to translate all that here. So we get y transpose py minus x transpose px, and then we get 2 times y px. So we get minus 2 times y transpose px, then 2 times x px, plus 2 times x transpose px. And this should be greater or equal than 0. Yeah? And there's this term, here is minus 1 times, here is 2 times. So we get like once. Yeah? And then we actually got the same expression before when we did it like from the definition. And then this is equal to x minus y, or y minus x, whatever. X minus y transpose p. And this has to be greater or equal than 0, and this is for all x and y. Yep. And then again, well, we got exactly the same expression as before. Yeah, x minus y transpose p, x minus y. And then we say, when is this true for all x and y? Well, it's true when p is positive semi-definite. Yeah? So this is equivalent to p positive semi-definite. Okay, the quadratic function is convex if and only if the quadratic term is positive semi-definite. Okay. Questions there? So the algebra gets a little bit simpler because we use this grading calculation is already including a lot of the algebra that we did last time. Okay? Now, what happens when we use this one? The Hessian one. Yeah, so that was the first order criterion. Let's use the second order criterion. And, okay, this is space should be enough. What does the second order says? I need to compute the Hessian. Now, what is the Hessian here? We have the gradient here, 2px cubed. So the gradient does not, Q doesn't have x, so the Hessian is just 2p. Yeah? And then the function is convex if and only the Hessian is PSD. And 2p is PSD if and only if p is PSD. Okay? And what really happens is, in this case, all the algebra that we did before is given in the proof. So we do it in the proof once, and then still you have to compute the Hessian. That's, let's say, the problem. If you want to show that a function is convex, now you have several tools. You can try the definition. You can try computing the gradient and proving that. You can try computing the Hessian. And then you have to show that a matrix is PSD, which is not an easy task. Yeah, to show that a matrix is PSD, you can try the definition of PSD, or you can try computing eigenvalues, but usually that's only possible when you have a numerical matrix. Yeah, not an analytical problem. And also, if you want to do that by hand, you can only do that when the matrix is size 2 by 2, maybe 3 by 3. Don't try ever 4 by 4. Okay? Or you can try doing some Cholesky decomposition. Like there are all these 4 definitions that we have. Yeah, but proving that a matrix is positive semi-definite is not easy in general. Yeah, numerically it's easy, meaning if you have a computer and you can throw it into a computer, then it's easy. Okay, but in general, so this criteria seems okay, very nice, but when you try to use it, still you need to show that the matrix is positive semi-definite. So they work both there. Okay. So there are different tricks, but yeah. But I guess also like you can try we saw that the maximum of convex is convex, so there are properties like that. The summation that okay. So let's see. So that was quadratic functions, then the second order property. This is what we just did, and then we got that P has to be perfect. Okay, what about this one? Let's show. Well, the question is this: when is this function convex for a given A? Yeah. This is the problem that you solve when you solve these squares. So here x is your betas, and A is your data, and B is your labels or your y values. Yeah, and then at the end you will solve this problem that looks like this: ax minus b in norm square. Yeah, that's the problem that you solve this square. So when is this function convex? So the question is, what criteria do you want to use? You want to use the definition? You want to use gradient? You want to use the Hessian? So usually using the definition is a lot of algebra. So let's try to compute the gradient to see how it goes. If it is too difficult, then we will try to use the definition. Yeah. So, before I run out of time, homework is coming out today. You, as part of your homework, you're going to prove that a function that is very difficult is convex. Yeah, but there is how to prove it. Okay, so you're going to against this one. It's just that I'm thinking that we might run out of time after we do this. So this is the last slide of these lectures. There are all these functions that are convex, and then the one that you're going to prove in the homework is this one. So here, this function has as inputs matrices. Yeah, and then the function is the logarithm of the determinant. Actually, I'm missing a minus here. It's a minus logarithm of the determinant. I think the homework is correct. Okay, so it's minus logarithm of the determinant. That function is convex. Okay, and you're going to show that. So it's scary, but it's not scary. You will see it in the homework. There is a trick there explaining it. And again, if you have questions, you can always ask, okay? And the point there is actually you are going to compute the gradient of this function. And that's the exercise that I really want you to compute that gradient. Okay? And the interesting part is this is a function defining matrices. So when you compute that gradient, this function depends on n square entries, well, really less because it's like half of them because it's on symmetry matrices. Yeah, so it's only like the triangle, fine. Yeah, so it depends really in n square halves inputs. So that gradient again, the gradient is a vector. But because we are representing the inputs as matrices, that gradient will end up being a matrix. Yeah? And you are going to, actually we tell you what is the answer and you have to show that that's the gradient. Okay? But again, we give you there hints and I don't want to scare you, and I'm trying to motivate you, but by your faces, you look like you're scared. Okay. But I have tried before and people like that problem. Okay, so let's do this. Let's do this one. So I'm giving the hint now. Okay, so we want to check if this function is convex. And then remember something important in the definition of convexity is that the domain of the function has to be convex. Yeah? Otherwise, let me give you an example of a function that is not convex. Yeah? If I say phi of t equal 1 over t, for example, this function is not convex because in the domain the function looks like this, and here it looks like this. Yeah, so if I assume the domain r minus 0, then this function is not convex. Now if I said, well, I want this function, but I want it not here, but on r plus. Sorry, the plus goes here. So that means I'm looking only at this part of the function. Then that function is convex. Okay? And why is that? Why do we care about the domain? Well, because otherwise you can have a function, let's say this one, f of t equal t cubed divided by t. Yeah? What is the domain of this function? all the points except 0. Why? Because when I evaluate that 0, I get 0 over 0. Yeah, so the plot of this function, I mean, we automatically think, oh, this is t squared. Yeah? Now, so the plot of this function is this, with the hole here, yeah? I know this is like in the brain, something in the back, like, oh, this was many years ago. Okay, but the plot of this function is this. When we say this is equal to t squared, we really mean this is equal to t squared, except when t is equal to 0. But this function is nice because we actually can fill out the hole, and then we get t squared. Yeah, but as it is written, this function is not defined there at 0, so it really has a hole there, and therefore it's not convex. Because if I take a point here and a point here, and then I say, let's say I put 1 and minus 1, and I take theta equal to a half, the definition of convexity doesn't hold because my function is not defined in this point. Okay? And that's why we need the domain of the function to be convex. Because we want that when we take 2 points, that segment is contained in the domain. Because otherwise, how do we evaluate that expression in the definition? Okay? Good. So the first thing that we need to do is to check the domain. So again, in the homework, the first thing that you need to do is to check the domain. And this is for the ones who come to the lecture. I mean, it will be posted later. So the domain is there in the slides. So you can just check and then check that your answer is correct. And then, okay, and then we want to do this one. So what is the domain of the function? So let me write here, f of x is equal to norm of ax minus b squared. What is the domain of f? So where is this function defined? I need to multiply by a matrix vector multiplication, that's not restricted anywhere, and then I have to take the norm square. That's not restricted, yeah? So the domain is the polar convex, yeah? Which is convex. So the domain is convex, okay? And now we have to apply our criteria. So, I mean, we can try with the definition, but let's try with the gradient. What is the gradient of f? Basically using this function, yeah, the norm square. What is the gradient of the norm square? Yeah.
Is it 2ax minus 2b?
2ax minus 2b, almost. What is the gradient of the norm square? Because this one you have right. You did this part correctly.
But
The gradient, so if I had the function norm of u squared, what is the gradient of that function?
use this number, like one dimensional. Or doesn't
No,
matter?
no, this is a vector, and I just doing the norm square, yeah. So like when A is identity and B is 0. Yeah, so
Just norm of u.
what is the answer that you got? You
The
got
norm of u.
2 times the what is inside, yeah?
Yeah.
Yeah, 2u.
Norm of u.
So this is the part that you did correctly. You are missing something in that. But you did this part. Okay? So the gradient of the norm square is 2u. Okay? Let's do that quickly. Norm of u squared. There, we did it the other day in a different way, but here, now we can do u1 squared plus un squared. Yeah, this is the two norm. And then if I do the partial derivatives, the gradient of that function is going to be 2 times u1, and then the second derivative will be 2 times u2, 2un, and this is 2. Yeah? And then that was the part that you got here. When you did the gradient, you said 2ax minus b. Yeah? Okay, good. But then, this is really applying the chain rule. You do the gradient of the norm squared. Now you have to take the inner derivative. Yeah? And the inner derivative is that a that is here, and you have to multiply by that. That's going to be a transpose. Okay? And please check this, because if you can do this algebra, then many things are it's not just about being able to do the algebra, but understand why is A transpose here and not A here, or why do I put it there in the left and why transpose. Okay? Yeah, so that was the part that you were missing here, the inner derivative. Okay, good. So we got that. Now what is the, so we did the gradient, let's do the Hessian. Yeah, and to do the Hessian, maybe it's better to write the gradient in this way. 2A transpose AX minus 2B. This part now does not depend on x, so this part is not going to appear in the Hessian, and this is the only part. And then, well, if this is the gradient, then the Hessian is going to be twice A transpose A. Yeah. Okay. Now we want to know whether the function is convex or not. So the question is, when is this guy positive semi-definite? The two doesn't matter. So when is A transpose A positive semi-definite? Yeah?
It's always good. All the elements are multiplied by the self-direct, so it says square.
Yes, actually this is the Cholesky decomposition. So if you look at the list of 5 items in the definition of PSD, one of them is the matrix can be written in this way. Yeah? Now why is that? So always. Okay. Why is that? Why is this positive semi-definite? Well, one of the definitions is if I pre-multiply by U transpose and I multiply by U, this has to be greater or equal than 0. Yeah? So this is PSD if and only if. So A transpose A PSD if and only if this happens. But what is this? Well, this is AU transpose AU. This is equal to that. Yeah? And this is norm square of AU. And then this is always greater than that. Yeah? Okay. Okay, so I know that is a lot of stuff. We started with that exercise, and then we had to compute this gradient, this Hessian, chain rule in multidimensional, this criteria for PSD. Okay, but it's just get familiar with that. That always helps. And then well, it helps to understand the problem. And then what this is really saying is this function is always convex.